Assalamualaikum. My name is Mohammad Akbar and me, along with my group members Sumaya Fahad and Musa Umair, have created a real-time helmet detector using Yolov11. Now, a question might arise that why this project? Workplace and construction site safety is a critical global concern. Every year, thousands of preventable head injuries occur because workers are not wearing helmets or because supervisors miss violations on CCTV cameras. Manual monitoring is labor-intensive, error-prone, and doesn't scale. By automating helmet detection with artificial intelligence, we can instantly flag violations, issue alerts, and even log non-compliance for later review. Practical applications of it include construction sites, manufacturing plants, smart cities, and mobile inspection apps. Our system handles images, videos, and live camera streams, making it versatile across desktop and edge deployments. Today, we will show you exactly how we set up, train, and run this model step by step. Now, the first step was verifying the GPU environment. Before training any deep network, we must confirm our computing environment can handle the workload. In Colab, we run this command and it queries the NVIDIA driver and shows the GPU details. Tesla T4, which is around 16 gigabytes of VRAM, driver version, and current memory usage. Why does it matter? Number one, speed. Training on GPU is way better and faster than training on CPU. Second is capacity. Larger models and bigger batch sizes require sufficient VRAM. Seeing the T4 listed confirms we can safely proceed with our YOLO V11 training without worrying about running out of hardware support. Second step is installing the dependencies. First, we install the Ultralytics package, which provides our YOLO V11 implementations, which is a simple YOLO CLI and a high-level Python API. Second, we install the RoboFlow, which streamlines dataset handling instead of manually uploading, organizing, and downloading images, which is a hassle. In doing this, we can simply fetch well-formatted data with a few lines of code. These installations take under a minute in Colab and set the stage for the rest of our pipeline. Then we perform some sanity checks. We import Ultralytics and then we check it. Then we also import YOLO from Ultralytics and image from ipython.display. Next step is fetching the data from RoboFlow. The exact dataset we have used for this project is the Helmet Detector Computer Vision project, and it contains around 13 classes, which include cycling helmet, half face, hard head, nutshell, quarter face helmet, etc. Now, how did we actually retrieve the data? First, we instantiate the RoboFlow client with our API key. Then we navigate to our workspace and project by name. Then we request version 1 of the dataset specifying the YOLO V11 export format. RoboFlow downloads a local folder containing data.yml and train, valid and test image and label subfolders. Finally, dataset.location prints local path so we can reference it in our training command. Now let's move towards the actual training of our data of our model. Now, a question might arise like why did we use YOLO YN and not YM or even Y11S? The actual reason was because of hardware restrictions. We did not have a dedicated GPU and we had to work in Colab. So obviously Colab has its restrictions, and 11N worked better than the other models because of again hardware restrictions. They couldn't run for a longer period of time. The second concern was that we had to implement it into a real time detection system. So again, because of hardware restrictions, we did not have a dedicated GPU, so 11S or 11M wouldn't work really smoothly, so 11N was a best choice. The second question is why did we train till 50 epochs? So by training multiple times, we came to see that 50 epochs was the sweet spot where we weren't compromising our accuracy and we were also preventing overfitting. First, we have task equal to detect, which specifies the object detection rather than classifications or segmentations. Then we have mode equals to train. It enters the training mode, inference, and export use. Mode equals to predict or mode equals to export. Then we provide it the data set location, and after that we provide it with our model, which is Yolov11.pt or Yolov9nano.pt. Then we provide it the 50 epochs, and which runs 50 full passes over the training data, which is sufficient for a small model to converge on a moderately sized dataset. Then lastly, we provided it with img sz equals to 640. It resizes all input images to 640 by 640 pixels for both training and validation. These settings strike a balance: nano variant for faster iteration, 50 epochs for adequate training, learning, and 640 resolution for moderate detail versus speed. Next, uh, we move towards visualizing our training diagnostics. First, we have a confusion matrix, and we can see clearly that helmet and then quarter face helmet and nutshell helmets work the best. They work the best among the other classes. Now, after this, Sumaya will explain the other parts of the code.
Hello, this is Sumaya. In this demo, I'll walk you through the important visual outputs and testing for our helmet detection project built using Yolov11. So let me just scroll down to section 8. That is basically visualize class level distribution. This graph here shows a number of label instances for each class in our dataset. You can see multiple helmet types like cycling helmet, modular helmet, and so on. It helps us verify if our dataset is balanced or if there are underrepresented classes, which is crucial for fair training. Now next to the right, we see bounding box, anchor distribution, and heat maps of label positions. These help us understand how objects are spatially spread across frames and whether annotation sizes are consistent. Now I'll scroll down to section 9, that is visualize loss and MAP curves. These training graphs are essential in evaluating the model's learning. The box loss and objectness loss graphs show how well the model learned to draw bounding boxes and detect objects. A gradually decreasing curve like this indicates good convergence. The MAP 50 and MAP 50 to 90 metrics below reflect accuracy. Higher values here indicate better performance. In our case, MAP values stabilize well, which means our model has learned to detect helmets reliably. Now moving to the section 10, that is prediction samples. These are randomly chosen validation images with predicted bounding boxes. We can see it correctly identifying helmets and labeling them with confidence scores. This step visually confirms that the model is working and predictions are accurate. Now let me show you the live video inference we have set up using OpenCV and Yolov11. We rewrote a small Python script. Each frame, as you can see in the video, each frame is passed to the YOLO model, which return prediction results like this bounding boxes around helmets with their detected class names. In the terminal output, you can see inference speed and object detection results per frame. It detects classes like helmet, cycling helmet, or quarter face helmet, and sometimes shows false detections like nutshell due to dataset labeling noise. Overall, the model works well in real time and achieves inference speeds of 35 meters per second per frame, which is fast enough for real world deployment. That concludes my demo. Thank you.
ये हमारी फाइल है जिसमें हमने हेलमेट को रियल टाइम में डिटेक्ट करवाया है। इसके लिए हमने दो लाइब्रेरीज यूज़ करी हैं। एक CV2, ये OpenCV की लाइब्रेरी है जो इमेज और वीडियो प्रोसेसिंग के लिए यूज़ हो रही है, और फिर हमने अल्ट्रा लेटेस्ट लाइब्रेरी का योलो मॉडल यूज़ करा है। अच्छा, ये मॉडल जो है यूज़ हो रहा है ताकि हम अपने मॉडल को लोड करवा सकें। जो भी हमने मॉडल ट्रेन किया है उसको हम लोड करवा सकें। फिर यहाँ पे हमने जब हेलमेट डिटेक्शन को फाइल को ट्रेन किया था, तो उसने हमें एक ट्रेन फाइल दी थी जिसका नाम था best1.pt। तो इस फाइल को हमने मॉडल के अंदर लोड करवा दिया। फिर हमने यहाँ पे आके अपना कैमरा ओपन किया, फिर हमने चेक किया कि हमारा कैमरा ओपन हुआ या नहीं। ये लाइन चेक करी कि हमारा कैमरा ओपन हुआ या नहीं। अगर कैमरा ओपन नहीं हुआ तो वो एरर दे दे, वरना आगे चले। फिर हमने यहाँ पे अपना लूप लगाया कि अगर जो भी यूज़र है वो जब तक कि क्यों नहीं दबा रहा तब तक चलते रहो। फिर हमने अपना वीडियो में से एक फ्रेम लिया और उसमें फ्रेम में लोड करवाया। तो जो भी फ्रेम था वो फ्रेम में लोड हो रहा था, और ये आरटीक बूलियन वेरिएबल है जो बता रहा है कि आपका फ्रेम लोड हुआ या नहीं। अगर नहीं हुआ तो लूप से बाहर निकल जाए। फिर अगर हमारा फ्रेम लोड हो चुका है तो फिर हमने उस फ्रेम को मॉडल को दिया, जो भी हमने मॉडल लोड करवाया था उसको दिया, और बोला कि चेक करके बताना कि वीडियो में हेलमेट है या नहीं। और जो भी रिज़ल्ट है वो रिज़ल्ट्स में सेव करवा दिया। अब रिज़ल्ट्स के अंदर बहुत सारे फ्रेम्स थे, तो ये जो 0 है ये पहले वाला फ्रेम जो है वो ले रहा है, और उसके अंदर प्लॉट कर रहा है। प्लॉट क्या कर रहा है, लेबल दे रहा है कि जो भी हमने ट्रेन करवाया था उसने जो भी लेबल्स दिए थे कि हेलमेट है, ये नटशेल है, जो भी है, तो वो लेबल बना के वीडियो में शो कर रहा है। तो हमने उस वाली जो फ्रेम है जिसमें लेबल्स वगैरह शो हो रहे थे उसको हमने एनोटेटेड फ्रेम में लोड कर दिया। फिर हमने ओपन सीवी का वो जो विंडो है वो खोली, और उसमें जो भी हमारा फ्रेम मिला था हमें प्लॉट वाला वो हमने शो करवा दिया, और उस फ्रेम का नाम दे दिया कि आप इसको एग्जिट करने के लिए क्यू दबा दें। फिर जो है हमने यहाँ पे यूज़र का वेट किया कि अगर यूज़र क्यू दबा देता है तो लूप से निकल जाओ, वरना फिर चलते रहो। अगर यूज़र ने क्यू दबा दिया फिर हमने यहाँ पे कैप डॉट रिलीज लगा दिया कि हमारा जो वेब कैम है उसको बंद कर दो, और ओपन सीवी के जितने भी मॉड्यूल्स हैं, जितने भी विंडोज़ हैं उनको क्लोज़ कर दो।